Dr. Sarah Williams studies a series of transparent acrylic tubes arranged in a zigzag pattern. Each section connects to the next via a specialized flexible coupling that allows for several degrees of controlled movement. Traditional tunnel design treats the structure as a rigid entity, Dr. Williams explains, adjusting the model's configuration. But that approach won't work for Gibraltar. We're developing articulated tunnel technology, sections that can accommodate seismic shifts while maintaining structural integrity. The model before her represents a tunnel that dances with the earth. Rather than a single continuous rigid tube, this design incorporates engineered flex points at strategic intervals. When subjected to seismic motion in the testing apparatus, these segments move in controlled ways, absorbing energy rather than transferring it through the entire structure. Each segment can shift up to 1.8 meters laterally and 0.9 meters vertically while maintaining watertight integrity, Dr. Williams says as she activates the simulation. The model subtly undulates as artificial seismic waves move through the test bed. This innovation addresses how to create a structure that can withstand both the constant pressure of hundreds of meters of seawater and the unpredictable movement of an active fault zone. The answer lies in decoupled design philosophy. Traditional tunnels rely on rigid connections, with segments locked into place. The Gibraltar design features specialized gasket systems made from composite materials that remain watertight even during substantial movement. We've tested prototypes under pressures exceeding 100 atmospheres while simultaneously subjecting them to lateral shifts, Dr. Williams notes. The latest iterations maintain perfect seals even under extreme conditions. Behind her, monitors display simulations showing stress distribution through various tunnel configurations. The team runs thousands of scenarios daily, incorporating the latest geological data from the seabed. Dr. Williams displays a cross-section diagram showing another revolutionary aspect: layered composite materials unlike anything used in previous tunnel projects. The tunnel segments themselves represent a major advancement in materials science, she explains. We're using carbon fiber reinforced polymer matrices with engineered failure points, areas designed to deform in specific ways before the critical structure is compromised. These materials provide extraordinary strength while exhibiting flexibility impossible with traditional concrete. They can withstand pressures 5 times greater than conventional materials while being 40% lighter. The tunnel's proposed walls consist of 5 distinct layers. The innermost passenger-facing surface incorporates self-healing polymers that seal minor cracks automatically by reacting with seawater. We've moved beyond resisting natural forces, Dr. Williams says. We're designing systems that adapt to them. The tunnel boring machines, TBMs, being developed for this project mark another breakthrough. In a facility in northern Spain, engineers are creating the Chimera, a hybrid tunneling system that integrates 3 distinct excavation technologies: mechanical cutting, hydro-excavation, and targeted microwave rock fracturing. The cutting head reconfigures itself based on real-time analysis of the rock formation, explains Dr. Alejandro Vega, lead mechanical engineer. When it encounters exceptionally hard zones, it switches to hydro-excavation. For the most resistant formations, we've developed a microwave system that selectively weakens rock. The machine continuously analyzes the material ahead, selecting the optimal approach for each section. This adaptive capability could potentially triple tunneling speeds through the most challenging sections. Environmental management within the tunnel presents its own challenges. At depths reaching 475 meters, conventional ventilation systems would struggle against extreme pressure differentials. We've designed a segmented ventilation approach with specialized pressure transition chambers every 3 kilometers, Dr. Williams explains. This creates manageable zones rather than attempting to ventilate the entire structure as a single unit. The design incorporates countercurrent heat exchange systems that capture waste heat from the tunneling process for environmental control, reducing operational energy demands by approximately 30%. Equally innovative is the real-time monitoring system being developed. Thousands of fiber optic sensors will be embedded throughout the structure, creating a neural network that can detect changes in strain, temperature, and humidity with extraordinary precision. We'll identify potential issues before they become critical, Dr. Williams says. The tunnel will tell us when and where maintenance is needed. This monitoring extends to seismic activity. Accelerometers throughout the tunnel will detect ground motion, triggering automated responses ranging from adjusting ventilation parameters to implementing emergency protocols. The entire structure is designed to be responsive rather than merely resistant, Dr. Williams emphasizes. It's a fundamental shift in infrastructure engineering. Significant challenges remain. The articulated segments must maintain perfect alignment for rail transport while allowing controlled movement during seismic events. Manufacturing processes for the advanced materials must be scaled to industrial levels. We've moved from asking, "Is this possible?" to "How do we optimize these solutions?" Dr. Williams acknowledges. With the 2030 World Cup deadline approaching, these technologies need to move from prototype to implementation within just 3 to 4 years. Yet every breakthrough brings the project closer to reality. The flexible joints, adaptive boring machines, and self-monitoring systems work together as a unified approach to the seemingly impossible. What once appeared an engineering fantasy now takes shape in laboratories and test facilities across Europe. What makes this project different is that we're developing entirely new approaches specifically tailored to Gibraltar's unique challenges, Dr. Williams says. The tunnel that dances with the Earth may soon transform from vision to reality. The cost-benefit equation. Beyond the engineering marvels lies the cold reality of numbers. At $6 billion minimum, this would rank among the most expensive infrastructure projects in history. But what if the true cost of not building it is even higher? Dr. Mohammed Al-Bakri adjusts his glasses as he scrutinizes the complex financial models on his screen. As the lead economist at the Mediterranean Economic Development Institute, he spent the last 15 years evaluating major infrastructure investments across 2 continents. What's fascinating about the Gibraltar crossing is the extraordinary economic equation it presents, Dr. Al-Bakri explains, gesturing toward his financial projections. We're looking at initial estimates between $5 to $20 billion, depending on which design is ultimately selected, with our current working model at the £6 billion mark. The variation stems from fundamental design decisions yet to be finalized. A submerged floating tunnel concept might come in at the lower end of our range, Al-Bakri notes, while a traditional bored tunnel with extensive safety systems could push us toward the upper limit, especially if we encounter unexpected geological complications. These figures place the Gibraltar crossing alongside other monumental projects like the Channel Tunnel, $16 billion in today's dollars, and Japan's Seikan Tunnel, $7 billion, though with potentially greater economic impact. The question isn't whether we can afford to build it, Dr. Al-Bakri argues, but whether we can afford not to. Our economic models suggest significant long-term returns that could transform both regional economies. The financing structure reflects the project's multinational nature, with 40% governmental funding split between Spain and Morocco, 30% from the European Union through infrastructure development funds, and 30% from private investors and development banks. This public-private partnership structure distributes both risk and reward, Al-Bakri explains. It also creates accountability. Private investors won't commit unless they see viable returns, which helps keep the project economically sound. Looking beyond construction costs reveals the true economic potential. Al-Bakri's team projects a 24% increase in bilateral trade between Morocco and Spain within 5 years, generating approximately €3.7 billion in new annual economic activity. The human impact would be substantial. creating 15,000 direct construction jobs and potentially 100,000 permanent positions across both countries. This isn't merely infrastructure, it's a bridge to prosperity for thousands of families, Al-Bakri emphasizes. Tourism shows particular promise. With Morocco currently receiving 13 million international tourists annually, economic models predict a 30% increase within a decade, injecting an additional €2.1 billion into the Moroccan economy each year. The psychological impact of a physical connection cannot be overstated, Al-Bakri emphasizes. When tourists can board a train in Madrid or Barcelona and arrive in Tangier or Casablanca without ever changing transportation modes, the perceived distance collapses. Spain stands to gain similarly, with North African tourists spending an estimated €1.8 billion annually in Spanish cities connected by the new rail link. Industrial development presents another major opportunity. Morocco has already established itself as a manufacturing hub, particularly in automotive and aerospace, Al-Bakri notes. The rail connection would allow just-in-time delivery of components between European and African production facilities, creating integrated manufacturing corridors that span continents. These manufacturing synergies could generate €5.2 billion in new economic activity annually, while creating approximately 27,000 direct manufacturing jobs across both countries. Not all economists share Al-Bakri's optimism. Dr. Elena Torres at the Barcelona Economic Policy Institute questions whether projected increases justify the massive investment. The fundamental question is whether this creates genuinely new economic activity or simply redirects existing commerce, Torres argues. Our analysis suggests that up to 65% of the projected increases represent shifts from other transportation modes rather than truly new economic relationships. Al-Bakri acknowledges these concerns but points to the Channel Tunnel as a precedent that transformed Britain-Europe relations beyond transportation efficiency, despite initial financial disappointments. The difference with Gibraltar is timing and context, Al-Bakri contends. The Gibraltar crossing would immediately connect two mature high-speed rail systems in an era of increasing African-European economic integration. Environmental benefits add another dimension to the economic equation. Rail transportation generates approximately 75% fewer carbon emissions per passenger compared to aviation, translating to €180 million in annual benefits and displacing approximately 870,000 tons of carbon emissions yearly. The regional impact could be transformative. Andalusia, with unemployment rates approaching 20%, could see a 3 to 4 percentage point reduction through new logistics hubs and supporting industries. Northern Morocco could experience GDP growth increases of 1.5 percentage points annually for at least a decade. This project connects two continents with fundamentally different economic profiles and complementary advantages, Al-Bakri emphasizes. That creates possibilities for economic synergy that simply don't exist with typical infrastructure projects. Return on investment timelines vary from 15 to 20 years in optimistic projections to 25 to 30 years in conservative ones, though broader economic benefits could accelerate societal returns. Major infrastructure investments are never solely about direct financial returns, Al-Bakri concludes. They're about enabling economic possibilities that wouldn't otherwise exist. The true measure of success will be whether the Gibraltar crossing fundamentally transforms the relationship between Europe and Africa from separate economic spheres to an integrated economic zone. Throughout history, humans have dreamed of conquering the unconquerable. The Gibraltar Strait represents our greatest remaining geographic challenge. 8 miles of seemingly impossible terrain. The spirit that built the pyramids, the Great Wall, and sent humans to the moon perseveres. As Dr. Al-Bakri reminds us, we don't build these monuments because they're easy, but because they redefine what's possible. Like a sunrise bridging two horizons, the continents await their connection. The day approaches when this dream becomes reality.